Hi everybody, Mrs. Pesic here,
And Miss Bella here.
and we are looking at section 3.2, which is on multiplying polynomials. The objectives are to multiply by polynomials and to use the binomial expansion to expand binomial expressions that are raised to positive integer powers. To multiply a polynomial by a monomial, you would use the distributive property and the properties of exponents. So let's take a look at this first example. We've got 4y squared times a binomial of y squared plus 3. So we just need to distribute. The 4y squared gets multiplied by y squared. So that's going to be 4 times y to the, remember if we're multiplying two numbers with the same base, we have to add their exponents. So that's going to be 2 plus 2 is 4. And then plus 4y squared times 3 is going to be 12y squared. So that's going to be our answer for this.
All right, let's try one more of those. Again, I want to find the product. So I have a monomial, a single term out front, and I'm going to distribute it into the three terms here. So first off, I have 3c d squared multiplied by 4c squared d. So that is going to become a 12. If I add my powers here, I have c to the first and c to the second, so c to the third, and you have d squared and d to the first, so also a d to the third there. When I multiply by the second part, I'm going to have plus 3cd squared multiplied by negative 6cd. So 3 times negative 6 will be a negative 18 or minus 18. I have a c to the first here and a c to the first here. So that becomes c to the second. Remember, I'm adding those. And then d squared and d to the first. So that becomes d to the third. For our last part here, again, I'm going to distribute to this outer term here. So plus 3cd squared multiplied by 14cd to the second. So 3 times 14 is going to be positive 42. If I look at my c terms, c to the first and c to the first is c to the second. And then I'll end up with d squared and d squared. If I multiply those, that becomes d to the fourth. So again, this would be the product that you get from multiplying all those together. Notice I cannot combine any of those because they're not like terms. I have my variables would all have to be the same in every term in order to combine them, but there are no no combination of the same CD in each of those.
Okay, so to multiply any two polynomials, use the distributive property and multiply each term in the second polynomial by each term in the first. So, for example, if we were going to multiply x plus 2 times x squared plus 4x minus 3, we would have to take the x and multiply it by all three of these, and we would have to take the 2 and multiply it by all three of these. And so there's really 6 separate multiplications that we would have to do. And that's what this is saying down here. Keep in mind that if one polynomial has m terms and the other polynomial has n terms, then the product has m times n terms before it is simplified. Like this had a total of 2 terms and this had a total of 3 terms, so we ended up having a product, or we're going to have a product of 2 times 3 or 6 terms by the time we're done. And it might be possible to combine some of those and it might not. So let's try this example. We're going to find the product. We're going to take the a and we're going to multiply it by all three of these. So that's going to be a times 2 plus a times a negative 5a plus a times a squared. And then we're going to want to also do negative 3 times 2 plus a negative 3 times a negative 5a plus negative 3 times a squared. So when we work this all out, we end up getting 2a minus, right here, minus, not minus 10, minus 5a squared plus a to the third. And then down here, the 3 times the negative 2 is a negative 6. And then we have here a positive 15a. And here we have a negative 3a squared. And if there are any like terms that we can combine, and I see that there's a 2a here and a 15a here. Let's combine those and we'll get a 17a. And let's see if I should put these in the right order first. I see an a cubed term. I'm going to put that first. And then I see some a squared terms. Here's a minus 5a squared and a negative 3a squared is going to be a negative 8 a squared. So I have that plus that 17a that we already had, and then I still have this one constant term here, minus 6. So this would be our product.
All right, let's try another one here. So we have y squared minus 7y plus 5, that polynomial, multiplied by y squared minus y minus 3. So if you notice, I'm going to start off with 3 terms in here and 3 terms in here. So I should have a total of 9 terms before I simplify. And so let's do this in a box method, which is another way that you can use when you are multiplying. So in order to do the box method, I'm going to take these 3 terms and I'm going to write them vertically. So y squared minus 7y plus 5. And I'm going to take these 3 terms and write them horizontally across the top. So y squared minus y minus 3. And we're literally just going to make a box and we're going to multiply in here. So we're going to multiply all of these terms together, so I end up with my 9 terms, and then we will combine any like terms that we see. All right, so how does the box work? Well, in this box right here, I'm going to multiply what I get from y squared times y squared. Well, y squared times y squared, if I add my powers, becomes y to the 4th. If I kind of want to move that over now and I want to figure out this one, well, again, it was what is in the row above it, which would be our negative y, what is kind of across from it to the left there, a y squared. So if I multiply the two of those, I'm going to end up with negative y to the 3rd. Again, I'm going to move over to this box here now. Again, how will I find that? Well, I'm going to take this negative 3 and I'm going to multiply it by this y squared. So that's going to end up being negative 3y squared. For the next part of my box, whoops, wrong thing I'm moving there. There we go. To get this one down here, well, now I'll take this value here multiplied by this value here. So I'm going to end up there with a negative 7y to the 3rd. Remember, this is the first. I'm adding my powers. For my next part of the box, I'll move this over and see what I'm multiplying by. So I'm going to have a negative 7y times a negative y, which will become a positive 7y squared. And then we'll be over at this part of the box, so kind of moving over what I'm using here. Negative 3 times negative 7y will be a positive 21y. All right, keep finishing and filling this out. So I'm going to move into this column and into this row. So I'm going to have positive 5y squared. Again, adjusting this one more time to see what we're working with. 5 times a negative y is negative 5y. And then finally, for this last one, I have a negative 3 times a positive 5, which is a negative 15. So I have all 9 of my terms, so it was a 3 by 3 box here. So my last goal is to combine like terms. Something that is nice about the box method is if you kind of take a look at this, things will line up on the diagonal. So if I want to notice, are there any things that have y to the same power? Well, this right here, negative 7y to the 3rd, and negative y to the 3rd right there, both have y cubed. Kind of moving over a step, 5y squared, positive 7y squared, and negative 3y squared. Again, same idea, negative 5y, 21y, and then I have y to the 4th up here, which doesn't have anything that matches it, and a negative 15 down here, which does not have anything that goes with that, no like terms. So what would be my final answer in standard form? Well, the highest power was y to the 4th, and there was only one term with that, so y to the 4th. For my y to the 3rds, again, I'm looking in my yellow highlighted boxes here and here. Negative 7y to the 3rd minus 1y to the 3rd will be minus 8y to the 3rd. My y squared terms are highlighted in green, so positive 5y squared plus 12y squared, or sorry, plus 7y squared is 12y squared. Minus 3 of those is going to be plus 9y squared. In this light blue, minus 5y plus 21y is plus 16y, and then finish off with my constant, which is negative 15. Again, this is just another method you can use. You could have used the box method on the other one, or if you wanted to, you could have just distributed this through 3 times, taken this through to each of those, and then finally that 5 to each of them, and combine all like terms that way. The box method is just an easier way, I think, to kind of organize your work and make sure you don't miss any terms.
Okay, so let's take a look at this example from the world of business. A standard Burley box is p feet by 3p feet by 4p feet. So let's kind of get a visual of what this standard Burley box is looking like. So we have a standard Burley box, and it is p feet by 3p feet by 4p feet. So I know that we could figure out the volume of this box by just taking length times width times height. That would be 4p. Oh, sorry. So slide this down. So it'd be 4p times p times 3p. So the volume would be 12p to the third. That would be our volume for this. But then the problem goes on to say that a large Burley box has 2 feet added to each dimension. So it's going to be a bigger box. 2 feet has been added to each dimension. So that large Burley box would be, instead of p, it would be p plus 2. Instead of 3p, it would be 3p plus 2. And instead of 4p, 4p plus 2. So if we want to write a polynomial v of p, kind of like f of x, v of p, in standard form that can be used to find the volume of the Burley box, the large Burley box, then we would really need to multiply 4p plus 2 times p plus 2 times 3p plus 2. All right, which is kind of what we have written here. But let's use what I've got here. So at this point, we are multiplying these all together. So I would suggest that we multiply these two right here first. And let's just use FOIL to multiply those. So if we do that, we would have first terms, 4p times p is 4p squared. Outer terms would be 4p times 2 is 8p. Inner terms would be 2p. And the last terms would be 2 times 2 gives us 4. So I can simplify this because I see that I do have some like terms here. So I think I would end up with 4p squared plus 10p plus 4. And then we still need to multiply that, though, by the 3p plus 2 right here. So we're going to multiply this by the 3p plus 2. And in order to do this, now I'm multiplying a trinomial, this has got 3 terms, by a binomial with 2 terms. So using that box method, I know that I'm going to have 3 by 2 box. So I'm going to put my 4p squared here, 10p here, 4 here. That's from my first polynomial that I'm multiplying, and then a 3p and the 2 here. All right, from that second polynomial. And so if I'm multiplying these together, again, 3p times the 4p squared, I'm going to have 12p cubed. The 3p here times the 10p is going to be 30p squared. And then the 3p times the 4 gives me 12p. And then when I move down here, I can't move that down. So when I move down here with the 2 times the 4p squared is going to be 8p squared. The 2 here times the 10p is going to be 20p, and then the 2 times the 4 gives us 8. Again, we can look at the like terms here. We've got 8p squared and the 30p squared, so those can be combined. And we have the 20p and the 12p, so those can be combined. So when we do this, we're going to have 12p cubed plus the 8p squared, and the 30p squared is going to be 38p squared. And then if we have the 20p and the 12p, that's going to be 32p. And then we are left with still just 8 as our constant. And so this would be our expression for the volume of the large Burley box in terms of p.
Okay, let's try to find the product of another one, but we're going to have to do some expansion first here. So we have the quantity a plus b to the third. So if we remember what it means to have...
Isn't that just equal to a to the third plus b to the third?
No, it is not. So let's make sure we take a look at what that means. That really means you have 3 copies. Remember what an exponent means. 3 copies of the same thing. So before you can do this, you need to rewrite a plus b times a plus b times a plus b. You need to write that 3 times here. Now I can go ahead and find the product. So similar to what Mrs. Pesic did on the page before, in order to multiply 3 terms together, you first have to multiply 2 of them together, and then we'll multiply that answer by the third. So since I have a binomial and a binomial, let's use FOIL for this first part. So if I do first times first, a times a is a squared. Outer will be plus a times b. Inner will be again plus a times b, and my outer b times b will be plus b squared. So I'll have this answer I get from here, from multiplying those two, which I will then need to multiply by this third a plus b. So let's bring that down. Let's simplify the blue a little bit first. So ab plus ab means that really we have a squared plus 2ab plus b squared. Okay, so we're going to take that trinomial now, three terms, multiply by this binomial here. Again, let's use the box method. So since I have three terms from the blue, two terms from the red, I know I'm going to need a box that has 6 spaces in here for us to fill in. Let's see, can I move that one over a little bit? No. Okay, that's fine. So across the top, since that's where I put the 3, this will be a squared, 2ab, b squared. Again, if it helps you to put the positives there, you can. You don't really need those. Just make sure if it was a negative, you would bring that along. And let's put a plus b here. Okay, so let's do our multiplication. Let's see if we can bring this down just a bit to have a little more room. And let me clarify, that is not a 6. Maybe let's make that a little bit better of a b before we start. That looks better. Okay, so in my first box, I'm going to take a squared times a, which would become a to the third. Moving over to the right, I have 2ab times the a out here. So again, remember, I add my powers. It's really a to the first and a to the first. So 2a squared b. Over to the right one more time, b squared times a. And let's keep them in order here. So ab squared. Down in the second row, we have a squared times b. So again, I'll say a squared b. Moving over to the right, 2ab times b. Again, that's b to the first. So 2a, and now I end up with b to the second because I added my exponents there. And finally, I have b squared times b to the first, which becomes b to the third. Again, using box method, we see some things that kind of match up here, have the same powers. So a squared b and a squared b's are there. And then I have ab squared here. So for my final answer, and I'm going to start with the highest power of a and work my way down here to write this in proper notation. I'll start off with a to the third plus, well, 1a squared b plus 2a squared b will give me 3a squared b plus my ab squareds. I have 1 or 2 there and 1 here. So again, plus 3ab squared, and finally b to the third. So this is the final expanded form of a plus b to the third. Remember, that was not equal to just distributing in that power. Okay, that is not a valid move there. You cannot do that. You have to write it 3 times instead and multiply those 3 together.
Okay, so before we go on, let's talk about Pascal's triangle a little bit. Pascal's triangle works like this. Starts with a 1, and then we keep the 1s down the diagonals, but what we do is we add the 2 numbers above to get the number below. So 1 plus 1 gives me 2 here, but I'm still going to have 1s on the edges. So here's a 1 again because it's on the edge, and then 1 plus 2 here is going to give me a 3 here. And then 2 plus 1 gives me a 3, and again 1 on the edge. So if we keep this process going, I get a 1, 1 plus 3 is 4, 3 plus 3 is 6, 3 plus 1 is 4, and then again a 1 on the edge. Let's do one more row of this. We get a 1 here, 1 plus 4 is 5, 4 plus 6 is 10, 6 plus 4 is 10, 4 plus 1 is 5, and again a 1 on the edge. This is called Pascal's triangle, and it's not just a fun thing to do on paper. It has a lot of really cool uses in math that keep showing up over and over and over again. This is considered row 0 of Pascal's triangle. This is row 1. This is row 2, and so on. And we're going to actually be able to do what we just did. Miss Bella did this problem, a plus b to the third, but we're actually going to be able to do this using Pascal's triangle a little bit easier. Notice that the coefficients on Miss Bella's final answer here were 1, 3, 3, and 1. And where does that show up? Wow, that's right here in row 3 of our Pascal's triangle. So let's take a look at how this works. So here's Pascal's triangle right here, just like we were doing. All right, those are the coefficients on Pascal's triangle, but it also helps to work with a binomial expansion. So if we are going to do a plus b quantity to the third, those coefficients are the numbers from the third row of Pascal's triangle. And so a plus b to the third, there's exactly the answer that Miss Bella just did using that kind of brute force method of multiplying the three binomials together. But we can use Pascal's triangle to help us do this a little bit easier. So each row of Pascal's triangle gives the coefficients of the corresponding binomial expansion. The pattern in the table can be extended to apply to the expansion of any binomial of the form a plus b raised to the n, where n is a whole number. So if we wanted to do a plus b to the fourth, that would be, giving us this row right here, a plus b to the fifth, and so on.
So just something you might want to add in. So one, you want to write down this table. I don't really think, maybe it's so as necessary to write all of this out, but I think it'd be helpful that you have this, and then you have what the coefficients would be, and why don't you add on one more column in your notes and say what row this is. So this is row 0, 1, 2, 3, 4, 5, etc. Notice that the exponent, so whatever power you are raising this to over here. So if I just kind of highlight those for you. So like 0, see right here I'm highlighting, those match exactly with what row it is. Okay, so it's kind of misleading. The 1 is not row 1. The 1, 1 is row 1. Okay, so keep that in mind. All right, so once you have that written down, let's go on to the next example. How are we going to use this? Well, when we want to do a binomial expansion, so again, two terms raised, added or subtracted raised to a power. Here's what we'll know. Number one, there will be n plus one term, so there'll be one more term than whatever the power is. The coefficients will be the numbers from the nth row of Pascal's triangle. So again, whatever power you're raising it to, whatever that number is, that is the row in Pascal's that you'll want to use for the coefficients. The exponent of a, so exponent of the first thing in the parentheses, the first term of the binomial, it will start with n. So it'll start with the highest power, and then the exponent will decrease by 1 in each successive term. For number 4, the exponent of b, the second term in the binomial, will start at 0, and then the exponent will increase by 1. And then finally for 5, the sum of the exponents in any term is n. So I think let's give that an example, and maybe that will help clarify what some of those things are. So for a here, I want to expand this. Again, I want to use Pascal's triangle. I don't want to just multiply. I know we just did an example before where I said this is really k minus 5 times k minus 5 times k minus 5. I do not want you to multiply that out 3 times. Instead, I want to see how can we use Pascal's triangle to help us out. So first thing I'm going to notice is I have k minus 5 to the third. So I need to figure out how does that match a plus b to the n so I can kind of match up with what I have. Well, a is going to be the k, b will be negative 5, and my n value is going to be 3. Again, so hopefully you see where all of those are matching up so I kind of know where I'm going to go from here. Okay, so the first thing I want to do is I know I'm using n equals 3. So that means I need to use the third row. Well, maybe I shouldn't call it the third row. We'll call it row 3. Okay, row 3 of Pascal's. So instead of rewriting that all out, I'm just going to flip back to the prior page for a second, and I'm going to look for row 3, which is right here. And again, that would become, I have something to the third in my power, which is what I have in this one. So my coefficients are 1, 3, 3, 1. So in this box, you'll notice that we have set up for you. Because I know it was row 3, I know I'm going to have n plus 1 term. So I knew I was going to have 4 terms. So that's why my box, or my box here has, 4 rows across. So I'm going to first fill out the coefficients, which were 1, 3, 3, 1. Okay, so we just did number 2 up there. We filled in the coefficients. Now it says number 3, the exponent of a. And we said that our a in this case is k. So the exponents of k are going to start with n, so start with 3, and are going to go down by 1 on each term. So in our second row here, we're going to end up with k raised to what power? Well, I'm going to start off with k raised to the third, because that was my highest exponent. Next, I'll go k to the second, then k to the first, and then k to the 0. And let's simplify those just a bit here, just so we know what we're working with. Whoops, didn't want that to happen. Let's see, can I just maybe shift this over in that box? No, okay, that's fine then, never mind. So this is really, I'll just rewrite it so we have some room. So k to the third. This is just k to the third, this is just k squared, this is just k. Remember, anything to the 0 power is just 1. All right, next up it says for number 4 that the term for b, so my b value was negative 5, so right here, it's going to start at the power of 0 and work its way up. So I'm going to have negative 5 to the 0, negative 5 to the first, negative 5 to the second, and negative 5 to the third. So if we simplify that, negative 5 to the 0, again, anything to the 0 power is 1. Negative 5 to the first is negative 5. Negative 5 squared is 25. And negative 5 to the third is negative 125. Now, how will I finish this up and figure out what this is altogether? Well, the last thing you need to do is multiply down each of these. So 1 times k to the third times 1 is k to the third. 3 times k squared times negative 5 is negative 15k squared. 3 times k times 25 is positive 75k. And 1 times negative 25 is negative 125. So if I were to move all of the stuff that we kind of decided work out of the way for a second, what would be my final answer of k minus 5 to the third? Well, it is k cubed minus 15k squared plus 75k minus 125. Again, this would be my final expanded binomial here, using Pascal's triangle rather than just multiplying it all together.
Yeah, it takes a while to explain it, but it is a much faster process than doing the brute force method. All right, let's try another example. Let's say we're going to do 3m minus 2 to the fifth. All right, so again, in this case, our a is 3m, our b is negative 2, and our n value is 5. So if its n value is 5, we had kind of a spoiler alert, we already have 6 rows here in our, or 6 columns here, but that's because we knew that we were going to be multiplying this out, and if this is n is 5, that means we want to go to the 5th row of Pascal's triangle, not 5th, we're going to call it row 5, row 5 of Pascal's triangle. But the idea, remember, is that if you're raising something to the 5th, you're going to end up with 6 terms. So that's why we had to have 6 columns to work with. So if we go back to Pascal's triangle right here, we want the 5th row, which is this row right here. So what's in the 5th row? I see 1, 5, 10, 10, 5, 1. That's row 5 of Pascal's triangle. So I'm just going to fill those values in right here. It was 1, 5, 10, 10, 5, 1. So first row is completed. Now we go to the second row where we take our a value, which in this case is 3m, and we're going to take 3m and we're going to raise it to this power right here. So 3m gets raised to the 5th. Then we're going to keep going down from there. So 3m to the 4th, 3m cubed, 3m quantity squared, 3m to the 1st, and 3m quantity to the 0. And so if we're working this out, 3m to the 5th is equal to 3 to the 5th is 243 m to the 3rd, and I'm sorry, m to the 5th, and I'm going to have to make it smaller or write it somewhere else maybe. But this is going to be 243 m to the 5th. I'm squeezing it in there. This one is going to be 81 m to the 4th. This next one is going to be 27 m to the 3rd. This next one is going to be 9m squared. And this next one is going to just be 3m. And last one, 3m raised to the 0 power. Anything raised to the 0 power is just 1. All right, so we've completed the second row. So now we want to go on to row 3, where we're going to take this negative 2, that's our b, and this b value gets raised to the 0 power first, then negative 2 to the 1st, then negative 2 to the 2nd, then negative 2 to the 3rd, negative 2 to the 4th. You see how we're just taking that same base, and instead of starting at 5 and going down to 0, we start at 0 and we go up to 5. And so let's simplify each of these. That was a negative 2. That was a negative 2 raised to the 0. Anything raised to the 0 is just 1. Negative 2 to the 1st is a negative 2. Negative 2 times negative 2 is a positive 4. Negative 2 times negative 2 times negative 2 is a negative 8. And negative 2 raised to the 4th is going to be a positive 16. And negative 2 raised to the 5th is going to be a negative 32. Notice that these went these went positive, negative, positive, negative, positive, negative. And they always will when you take a negative number to various increasing powers. All right, so our last column, we're going to be taking the product down this row. So we're going to take 1 times 243 m to the 5th times 1. And when we do that, we end up getting 243 m to the 5th. And then when we do the same thing in the next, it's not going to let me move that, is it? And when we do that in the next row, I'm taking 5 times 81 m to the 4th times a negative 2. And when we do that, we get negative 810 m to the 4th. And you can be checking that on your calculator. And then in our next term, we're going to have 10 times 27 m to the 3rd times 4. And that one turns out to be 1080 times m to the 3rd. And then in our next, we get 10, we're going to take 10 times 9m squared times a negative 8, which is negative 720. Is that right? Negative 720 m to the 2nd. And then in our next, we have 5 times 3 to the m times 16. So what is that, 240? All right, that gives me 240 times m. And then lastly, I have 1 times a negative 32. So that's just giving me, a negative 32. So all together with this, our final answer for this problem is going to be 243 m to the 5th minus 810 m to the 4th plus 1080 m to the 3rd minus 720 m squared plus 240 m minus 32. Now, I mean, this did take a long time, but I think it would take a lot longer if we were going to be doing a brute force method of multiplying out, 3m minus 2 times 3m minus 2 times 3m minus 2 5 times. So again, this is 3m minus 2 raised to the 5th is going to equal all of this.
All right, we have one last one we're going to do just to make sure we understand what's happening here. So we have the quantity 3x plus 1 to the 4th. So my a, try that again. Oh, there it showed up. All right, your a is 3x, your b is positive 1, and n is 4, which means we're row 4 of Pascal's. So let's go back and find that first. So row 4 of Pascal's will be, I'm just going to move the table down. Nope, that didn't work because now my rows don't match. There we go, row 4. So 1, 4, 6, 4, 1. Again, notice there are going to be 5 terms in that one because there's row 4, so 1 plus that. So 1, 4, 6, 4, 1. So let's fill that in first. Okay, so next up we're going to start with a, which was 3x, and we're going to start off by raising it to the 4th. So 3x to the 4th, 3x to the 3rd, 3x to the 2nd, 3x to the 1st, 3x to the 0. All right, 3x to the 4th is going to give us 81x to the 4th. 3x to the 3rd will give us 27x to the 3rd. 3x to the 2nd is 9x squared. 3x to the 1st is just 3x. And the quantity 3x to the 0 is 1. Remember, anything to the 0 power is 1. Next up, we have b to the 1st. So I'm going to start off with 1 to the 0, 1 to the 1st, 1 to the 2nd, 1 to the 3rd, and 1 to the 4th. Well, 1 to the 0 power, anything to the 0 power is 1. 1 to the 1st is 1. 1 to the 2nd is 1. 1 to the 3rd is 1. And 1 to the 4th is 1. So we are already ready to multiply down. So I'm going to take my first column here, 1 times 81x to the 4th times 1 will just give us 81x to the 4th. Next column, we're going to have 4 times 27x to the 3rd times 1 is going to give us positive 108x to the third. Next up, we're going to have 6 times 9x squared times 1, which will be positive 54x to the second. Moving on to the next column here, we're going to have 4. Oh, that's kind of hard to read. So 4 times, let's go back to yellow here. 4 times 3x times 1. That will give us a positive 12x. And then finally, we're going to end up here with 1 times 1 times 1, which will be nice and will just lead us back to a positive 1. So again, what does this lead us with? That the quantity of 3x plus 1 to the fourth is equal to 81x to the fourth plus 108x to the third plus 54x squared plus 12x plus 1. Remember, that's already in standard form. And again, using the binomial expansion with Pascal's triangle will already collect like terms for you and will leave you in standard form. You won't need to reorder that. All right, well, that is the end of our notes. So thank you for watching.
Have a good day.